So our lesson for quadratic modeling is a follow-up to us graphing quadratic equations by hand. We're going to be using a lot of graphing calculator today, so this lesson is heavily based with the use of a TI-84 CE color edition screen. You don't have to use a TI-84 CE, just any TI graphing calculator will do. So first we're going to talk about the projectile motion function, and we're going to see this function a lot in our work. We live in America, and we're gonna talk in a second about what the -16 is, but typically for these problems, this is for any object that is kicked, thrown, launched, hit, anything that has projectile motion. Some people in our department refer to them as throw-up problems. So when you throw a ball up in the air, shoot an arrow into the air, throw a football into the air. So a lot of this can be modeled with a quadratic function such as this. So the h at the beginning of the equation, which all these variables can change depending on your problem, if you're in a science class, even within this lesson, I think they change. H represents I'm going to call it the final height. Whoops, I can spell today. The final height of the object, but that doesn't necessarily mean the ground, because sometimes you don't want the object to hit the ground. T represents, I'm sure you guessed it by now, but it's time. Yeah, sketchy today. All right, time, and then for this, the way this model is set up, it is measured in seconds. Feet, by the way, height is measured in feet for this model. V sub naught, anything with a little zero subscript, represents an initial of whatever you're referring to. So V stands for velocity. So this is the initial velocity of which the object is thrown or kicked or hit or whatever. And then H sub naught represents the the initial height. And I should be labeling this. For this particular model, initial height is also measured in feet, just like the final height. And then initial velocity will be measured in feet per second. So sometimes if you're looking through a problem and you're trying to figure out, what this clue is, if you look at the label, it'll tell you. So there's a coefficient of -16 that we haven't really discussed yet. And this is going to be a given for our particular setup of this function. And that's because the -16 is the acceleration due to gravity. And then this is on Earth. We have to kind of specify that, because if you go to another space body, you have a different acceleration due to gravity. And then also it's in America, specifically because we are pretty much the only country in the world who still measures in feet. So if we are in every other country, so not the US, we're going to be measuring in metric more than likely. So instead of measuring in feet, they measure in meters, still per second. But since it's measured in meters, the -16 coefficient is going to change to a -9.8 meters per second squared. Okay, so big difference. So this particular problem must be done in America with being measured in feet per second. So they gave us a bunch of clues. It says it was thrown upward at a 45 feet per second. That's an initial velocity from a platform that is 70 feet high. So this is our initial height. And then they were really nice to you and they already went ahead and filled in the equation. And this is a case of where they, instead of calling the beginning of the equation h, they called it s of t. So they're using function notation, and you see this a lot in math textbooks. S represents like a positional function. Technically, you're measuring the position of the object at any given moment in time. And when they say position, they're referring to height. So s of t is just function notation. And it means the same thing as the h from our initial formula I gave you. So I already kind of answered these first few questions. What's the initial velocity? Or the first question. The initial velocity was 45 feet per second. And then the maximum height is something we're going to have to calculate. Now technically we can calculate this algebraically. It's just the vertex of the parabola. However, you have a lovely graphing calculator. It costs a lot of money. Let's use it. So clear out whatever the last function was, we don't want it, and then type in your new function. In this mode, your calculator is going to default the variable to an x, even though the formula wanted a t, it doesn't matter. It was 70, I believe, per second for velocity. No, that's not right. It's 45. mega. 45 feet per second with an initial height of 70. So very important we put the correct numbers in the right spot, Abruzzo. All right, now I can guarantee whatever window you have is probably not going to work. So think about what x represents. X represents the time that has elapsed. So right now I have it set up to go negative 10 seconds in the past. Well, that doesn't make any sense. So let's start at 0 seconds. And then we're going to go 10 seconds into the future. It's probably going to be too big. I don't really know anything about this rocket, but I have a feeling that 10 seconds is too far. Now, as far as height, I don't really know anything about this rocket. But negative 10 feet would be negative 10 feet underground. So you are welcome to keep that. There's nothing wrong with having your window go a little bit beyond what you really want to see for the real life problem. So I'm actually going to keep it at negative 10, but I'm pretty sure 10 feet is not tall enough because remember our rocket started at a platform 70 feet up in the air. So I'm going to make the Y max go to like, try 100. And then I'm going to hit graph and see what we're working with. You know what? Not bad. One thing I noticed is I went way too far out in the domain. I'm going to bring it back to like 5. And then I just need to go a little bit higher in the Y. So pull my domain back to 5. And whoop, I was so close with 100. Let's just go like 120. Say we're good after that. There we go. So this is the positional function for our rocket at any given moment in time. We're measuring time along this axis and then the height of the rocket along this axis. So when they say what is the maximum height that the rocket reached, we got to find this maximum here. So we're going to go to what's called the calc menu, which is underneath or right above our trace menu. So second, trace, and then we're finding a maximum. So it makes sense to choose maximum. And then left bound. Now, my emulator has a really bad lag. So you can just use your left arrow and get your cursor over here somewhere. I'm going to make mine jump to over here. So I notice if I need it to land here, that would be an X value of like 0.5 roughly. So I'm just going to type 0.5 and then hit enter. Now, if you dragged it over to the left side, once you drag it over to the left side and you get there, you got to hit enter to submit that point. So now it switches to right bound. So you need to either use your right arrow to cursor over, drag it to the right of the vertex. But mine is too slow, so I'm going to make it jump. And if I think about this as being x equals 2, that would be far enough. So I'm just going to make it jump to x equals 2. And then as long as the thing you're trying to find is in between these two submission points here, these vertical lines, then you're good to go. So when it says guess, just hit enter one more time. And it gives you a maximum of roughly 1.4, 101.6. So, I mean, think about what you're measuring here and think about the logic of it. Sometimes I get kids who say, the rocket reached a maximum height of 1.4 feet. That's just weird because didn't the rocket start 70 feet up in the air? So that doesn't even make sense. So remember, X is measuring time and this is the height of the rocket. So when I specifically say what is the height of the rocket, you need to answer that specifically as well. Maximum height of the rocket was 101.6, please label feet. And then how many seconds have elapsed by the time it gets to that maximum height? And I believe that was 1.4 seconds. So this next part of the question, they want you to figure out the height of the rocket at 1 second, at 2 seconds, and at 3 seconds. So you could manually plug in 1 and 2 and 3 for t, or remember our calculator here, if you just go to your table, this is like a bunch of points already plugged in for you. I have my table on auto mode where it auto fills. But if I look down, and I need to scroll down a little bit further in my tables, get down there a little bit. I see at 1 second it's at 99 feet, at 2 seconds it's 96 feet, and at 3 seconds it's 61 feet. So I'm just going to pull those points off the table. This is just a shortcut. Instead of having me plug them all in, the calculator already did it for me. So 99 feet, 96 feet, and 61 feet. The next part of the question says, find the average rate of change from 1 second to 3 seconds. So essentially what they want you to do is if you look at the graph, 1 second is right here, and then 3 seconds is like right here. And they want you to find, the average rate of change, which is a fancy talk for slope. Now, it's not going to be a super amazing representation of what the rocket is really doing from 1 second to 3 seconds. It's an average. And this is actually a calculus concept. But when you move on to pre-calc, you're going to talk more about what happens when you bring that average rate of change, domain a little closer together. But average rate of change is just you finding slope. So it's going to be the change in our y is measuring height divided by the change in time. So the change in height at 1 second to 3 seconds, order doesn't matter as long as you keep the same order. So if I do 99 minus 61, the change in time would have been 1 minus 3. So that is, let's see, 38 divided by -2, which gives me -19. And then remember the label was feet over seconds. So feet per second. So the average rate of change indicates that between 1 and 3 seconds, your rocket was dropping 19 feet per second. But like if we look at the graph, that doesn't make a ton of sense because it was still on the incline for a little while here until it got to 1.4 seconds. So that's why we say average rate of change over like a large spread like that isn't a real great indication of what's happening, but it's just a skill we want you to practice. Finding the average rate of change on a nonlinear function is essentially just finding slope between 2 points. So huge concept in pre-calc and calculus. And I'm sure you'll see it again. All right, this next question says, what happens if instead of launching the object, I just drop it? So if you think about your formula, remember it was h equals, and this is measured in feet, so American question, -16 t squared plus my initial velocity times t plus my initial height. So because we're not launching it, this entire term in the middle is going to be 0 because there's no initial velocity. So the formula is just -16 t squared plus initial height. So final height equals -16 t squared, and then our initial height is dropping it off of a 120-foot building. So they want a sketch of what this function looks like. So I already have my calculator open. Let's go ahead and use that. And sometimes when you do a bunch of these problems in a row, you don't have to keep changing your window, which is nice. But it's okay. We'll adjust it as we go. -16 x squared. Remember, it was plus 120. And I'm going to go out on a limb and say, what happens if I just hit graph? Is the window, window's close. I could do a few things. I could raise this window up a little bit, so I could, and I could also pull the x back a little bit. So shorten my domain to, let's just go to 4 seconds. And then the height of 120 was like right at the top there. So let's just go a little bigger with 130. So that would be a good representation of a sketch. So on your paper, you would sketch that. And when you sketch things for me, you want to do some labeling, okay? This was measuring in 1, 2, 3, 4 seconds. Time in seconds. And then up here, remember we went up to 130. Started, well, technically this is 0, but it was 0. Hello. All right. So our sketch, oh gosh, I forgot where it crossed. It crossed a little bit, really close to 3. Something like that. All right. So the idea is now they're going to want you to find how long will it take the object to reach its desired height. They want it to hit the ground. So basically they want us to find this part right here. Well, go back to your calculator. In order to find this point, that's clearly not a maximum. That's not even a minimum of our function. This is what we call a 0 of our function because we're asking what happens when you solve the equation or you set it equal to 0. So back to that calc menu. And if you choose the second one, and now we're going to follow the directions. So it says left bound. You just need to make sure your cursor is to the left of that 0, which it is. So I'm just going to hit enter. And now I need to drag it so it's a little bit to the right of the 0. Basically what you're trying to do is give your calculator a positive and then a negative submission point so that way it can do some calculus. Which, there we go. See? Heck. Still going. Mine I told you mine has a lag. Okay, I did hit enter, and then now you see these two vertical lines. These are the 2 points that I submitted, and then my 0 is right in between them, so perfect. So when it says guess, hit enter one more time. Get 2.74, it doesn't say where to round, so we'll just say 2.4 seconds. Now, I'll be honest, I don't think solving that with a calculator was the best way to go, because if my final height was the ground, wouldn't this be super easy to solve with algebra? You would just add this term over. There's only one t in the problem, so if you divided by 16, whatever that is, and then you ended up square rooting. Now, algebraically, you get plus and minus 2.74 seconds, but it doesn't make sense to say negative 2.74 seconds is when it hit the ground. So this is a case where algebraically a solution might show up, but it's extraneous for the context of the problem. So either way, you still get 2.74. So it's up to you. Sometimes you'll find calculators, while they're cool and neat, they're not always the most efficient way. All right, so what happens if we're not in America? What if we're anywhere else in the world? Well, remember our formula changes. It still is the final height, but instead of negative 16, now it's negative 9.8 because we're measuring in meters per second. So negative 9.8 t squared. It's still going to be initial velocity, but now measured in meters per second. And then still going to be our initial height measured in meters. So we're in a European basketball league, and the ball is at a height of 1.9 meters. That's my initial height. And then an initial velocity of 8.1. How many seconds until it reaches the rim, which is 3.05 meters high. So that's going to be my final height in this problem. So final height of 3.05 equals negative 9.8 t squared plus initial velocity of 8.1 t plus my initial height of 1.9. So if we were to solve this algebraically, this would not be a lot of fun. We actually haven't taught you guys how to do a lot of quadratic algebraic solving yet. So instead, we're going to use our calculator. And what I'm going to do, I'm going to actually type two functions in. One of these functions, one side of the function equation is going to go into y1, and the other one's going to go into y2. It doesn't matter which one goes into y1 and which one goes into y2. No. Hear that. Negative 9.8. Remember, it's going to change it to x for the variable, and that's okay. Plus 0.1 x, and then initial height of, I think it was 1.9. I should double check this. Yeah, all right. And then 3.05 is my target height for the rim. So put that into the other function. And then remember, our window is all messed up from the last question, so I can guarantee you this is not going to be an appropriate window. So let's just change this. It sounds like we're just shooting a basketball, so 0 seconds to 4 seconds, I think that's probably okay. But the height is really messed up. I don't really care about going negative 10 feet underneath the ground, so let's just start at 0 for the height. But 130 meters is way too high. So let's just go to like 5 meters. Let's see if that works. Yeah, and that was way plenty. So what I'm going to do is I'm actually going to pull this back a little bit. I'm just going to say 2 seconds. And I think my height was fine, actually. There we go. Okay. So this red line is the target height of 3.05. And you'll notice that it reaches that height twice. So you have to think about when you shoot a basketball, you know, it starts off at whatever level you're shooting it from, and then it arcs up and then comes back down and then hits the rim. Hopefully the net. So the question is, how many seconds until it reaches the hoop? They need us to figure out this guy right here, figure out what point that is, and then remember you're going to get an ordered pair, and once we find that ordered pair, we have to decide like what that means. So this time we're finding what's called an intersection. We have two functions, they're going to intersect each other, so go back to that calc menu, choose intersect this time, which is the fifth one, and then it says, is this your first curve? And notice it's blinking on the blue guy, and you go yes by hitting enter. And it says, is this your second curve? And you say yes by hitting enter. And then it says guess. Now remember, there's two intersections, so as long as you're closer to the one that you want to find, it's going to find that one by default. So I am closer to that one. I'm just going to hit enter one more time. And apparently, the ordered pair is roughly 0.6, 3.05. So remember what we're measuring. The x is time, and then the y is height. So when it says, when will it hit the rim, 0.6 seconds. And I apologize, I never got that sketch in, but you know, you guys are gonna, one of these. Yuck. Alright, and then you get a line, remember, intersect it. Oh, I should have used a different color. This line at 3.05. And then, you know, you wanted to find that intersection point, not this first one. Hopefully your line looks a little better than mine. Ugh, it's ugly. Alright. And then this is a question where they have you set up a lot in the algebra textbook, and I don't know why, because it's a pretty boring question. So definitely a non-real world problem, but whatever, we'll do it. All right, so the area of a rectangle is 105, and they don't tell me the dimensions of the rectangle. Now, I know this is a lot easier to solve just by guess and check, and you're assuming when you guess and check that it's going to have a nice set of answers. So not always going to have nice answers, we have to remember that. But also, we're just kind of practicing using the graphing calculator for setting up quadratic models. So let's practice. The way we find an area of any rectangle is we take the length and multiply it by the width. So for our rectangle, if we were to multiply length and width together, it'd be x times 2x plus 1. And I know the area should come out to 105. So if we're practicing using the graphing calculator, this is actually a good setup for it. Just like with the basketball problem, we're going to set up one function into y1, and then the other function into y2, and then we're going to find the intersection. So let's get all that mess out of there. Get your old functions out. We don't want them anymore. Type your new functions in. So it was, I already forgot, 105. They can go anywhere in the y equals menu. It doesn't matter. For our color screens, it's just going to change the color depending on where you go. It was x. You don't even have to simplify. Just x times 2x plus 1. Now, I can guarantee our window's probably not going to work. So, and think about it. One of the functions was y equals 105, and I'm only showing y's from 0 to 5. Like, I'm not even close to the right window. So I'm going to make my x's go a little larger because they do represent the length of the rectangle. And I'm feeling like 2 is too small, so let's go to 10. It is a bit of a guess, but we'll get there. Now remember, I wanted to intersect at 105. So as long as my window shows a little above and below 105, you're fine. So I'm going to go 100 for a y minimum. I'm going to go 110 for a y maximum. And then when I hit graph, if I can see an intersection, I'm good. Oh, perfect. So we need to find this point right here, which is an intersection. We're going to the calc menu. Number 5. And then it says, is this your first curve? I don't know if you can tell, but it's on the blue curve. It shows the blue one right here. Enter. And then it says, is this your second curve? You go, yeah, enter. And then it goes, is this your guess? Sure. Enter. And this intersection point is at x equals 7, y equals 105. So remember, x represents the length of the rectangle, or width, or whatever you call it. Doesn't matter. And then the y represents the area. Well, we already knew the area was 105, but now we know that the x measurement of that rectangle is 7. So if x equals 7, then this is 7, but when I plug a 7 in right there, I get 15. The dimensions of our rectangle are 7 meters by 15 meters. So again, I have a lot of kids who say, I guess and checked my weight and I got that same answer. I said, that's great, but we're practicing the quadratic modeling features on the calculator, so you do want to practice it as much as possible, especially when our answers are typically not nice answers. All right, keep at it.